If we look at the record of global temperatures over the last 150 years or so, we see a complicated pattern where temperatures fluctuated in the latter part of the 19th century and then rose from about 1910 up until 1940 or so. From 1940 through the mid-70s, temperatures plateaued as what's often referred to as a hiatus. And then from the mid-70s until about 2000, temperatures rose very, very steeply. Since 2000, there's been another hiatus and temperatures have been relatively constant. One of the big discussions around climate change has been whether this recent warming can actually be attributed to the rise in carbon dioxide. Now, we've already discussed how we shouldn't necessarily expect temperatures to rise exactly following the pattern of carbon dioxide in the atmosphere, because there are other factors like sulfate aerosols from burning of coal and burning of sulfur-rich diesel fuel, and a variety of other effects like heat uptake by the oceans. But a fundamental question is still, can we actually say that the recent pattern of warming is driven by the greenhouse gas addition to the atmosphere? One way to approach this has been to look at paleoclimate records over the last 1,000 years or so to see if we can put this recent rise in global temperature in a broader context. One of the most famous efforts to do this was done by a scientist named Michael Mann, who now teaches at Penn State University. Mike produced this curve in the late 1990s, where he combined the instrumental record of temperature over the last 150 years with a variety of proxy records of ancient temperature, including from tree ring records and from ice cores. You can see his paleo reconstruction of temperatures over the last 1,000 years in black, with some estimate of the error shown in yellow. As you would expect, the errors get pretty large as you go back over the last 1,000 years. In red is the instrumental temperature record showing the most recent rise in global temperature. This curve is often called the hockey stick because it looks a little bit like a hockey stick, with the blade being the more recent rise in the instrumental record. It shows a general cooling trend over the last 1,000 years with some fluctuations, but nothing that looks like the most recent rise in global temperature over the last 150 years. Now, there's been a lot of argument about whether temperatures 1,000 years ago were comparable to what they are today. And you can see that it's possible that temperatures going back 1,000 years were similar to what they are today, certainly within the error of the analysis. In addition, Mann's work was heavily scrutinized by statisticians who argued that some of the statistical methods he used to combine the different data sets were inappropriate. Some other studies have actually taken a slightly different approach. Rather than trying to combine all of the proxy reconstructions of climate over the last couple thousand years, this one study by Jonathan Overpeck and his colleagues looked at how different individual records changed over the last 2,000 years, in this case from the Arctic. What they showed was that the tree rings, the ice cores, and the lake sediments all showed a very similar pattern where temperatures slowly cooled in the Arctic over the last 2,000 years until the most recent warming trend over the last 100 years or so. I find it actually a little bit more compelling to see these records separated because the agreement between them is very compelling evidence that they're actually showing a coherent trend and that what they're reconstructing is robust. One of the claims by some of the people who deny that anthropogenic climate change exists is that the recent warming we've seen is actually due to changes in the activity of the sun. Now, I find this a little bit amusing because, in fact, the implications of this hypothesis are actually very dire for anthropogenic climate change. Let me explain. We know a lot about how the sun has varied over the last 500 years, at least since the time of Galileo, who first started making observations with his telescopes. Indeed, there was a period in the late 1600s called the Maunder Minimum, where we think there were very few sunspot cycles, and this resulted in a cooler sun and less solar radiation reaching the Earth, and it may be associated with a time in Europe called the Little Ice Age. Nothing like the last glacial maximum, but really a dramatic cooling in Europe that was a big deal if you were a farmer in southern Europe. We don't yet know how much of a global impact the Little Ice Age had. What's pretty clear, though, is that the magnitude of the radiative forcing associated with the Little Ice Age and solar variability over the last 100 years is actually pretty small. We think it's something like 1/10 of a watt per meter squared. Now remember that it's possible that much of the radiative impact of greenhouse gases has been canceled by putting sulfate aerosols into the atmosphere from burning of sulfur-rich coal and also sulfur-rich liquid fuel that we use currently for ships or diesel fuel in some parts of the world. There's a lot of uncertainty on exactly how big of an effect these sulfate aerosols have, but it is certainly possible that they've largely canceled out the effects of CO2, and therefore that the net radiative forcing is very, very small. So here's the irony. If the solar variability really is responsible for the recent warming we've seen, it actually implies a very high climate sensitivity. What it says is that there are huge feedbacks in the Earth's climate system that amplify this very small radiative forcing from the sun that we know is only about 1/10 of a watt per meter squared to give us this huge change in global temperature that we've seen over the last 100 years. Because we know that sulfate aerosols have a relatively short lifetime in the atmosphere and the carbon dioxide accumulates for very long periods of time, indeed a lot of it's going to be there for tens of thousands of years, it means that in the long run the greenhouse effect of CO2 is ultimately going to win, and the radiative forcing is going to be much, much larger than the small radiative forcing associated with changes in the sun. So if indeed the recent warming can be explained by solar variability, it means we're actually in very big trouble. That's the irony that I think that the climate deniers don't often understand, that actually that if they are correct, it means that global warming is going to be much worse than anybody thinks. Of course, the argument about what causes the recent warming is a little bit silly given a set of other observations that we have, which are from the tropical ice sheets at high altitude all over the world's mountains near the equator. The climate scientist who's really pioneered the study of tropical ice sheets is a man named Lonnie Thompson from Ohio State University. He's really been a superhero, sacrificing his own body to really bring back these archives that demonstrate that the recent warming we've seen is not part of some natural cycle and can't be explained by 100 or 1,000-year cycles of variability in the sun or in volcanoes or anything else, but that really has to be associated with the recent rise in carbon dioxide and connected to human-induced climate change. One of the ways that climate change is going to most impact human society is through sea level rise, at least for those people who are living near the coast. There are many different reasons for sea level rise in any one place. We often hear about the polar ice sheets, for example, and how they might melt, and that would cause sea level rise, and that's certainly a big concern. The largest source of sea level rise thus far has actually been the warming of the ocean and the thermal expansion of seawater, which causes the oceans to rise as well. But there are other factors as well. Locally, sea level can change because of the uplift of land or the subsidence of land that causes the relative sea level to rise or fall. And then you can actually change global sea level if you change the amount of groundwater that you pump out of the earth and dump into rivers and streams that ultimately run off into the ocean. So there are many different factors that affect sea level change, and we're going to take a look at some of these in a historical context. Most of our information over the last 100 years or so of sea level comes from tide gauges all over the world. Now, this is a really complicated data set because tide gauges are recording the local sea level at any one point in time. And as we said, different places on the land can be rising or falling because of geologic processes completely separate from a global sea level change. So, for example, sea level in the Gulf Coast, because of a lot of oil extraction, sea level's been rising partly because the land has been subsiding. The same is true in Venice, Italy, for example. If you put all the tide gauge records together and try to correct for the local effects like subsidence or uplift, What you see is a steady trend of sea level rise since about 1930 at a total rate of a little less than 2 millimeters a year. It's not completely smooth. There's some times when sea level rose faster for a few years and then slowed down for a few years, but in general it's a pretty linear trend since 1930. If you look, however, at the most recent data, just over the last 15 years or so, there appears to be a slight acceleration of sea level rise. Now, it turns out that over the last 15 years, we actually have much better data than the tide gauges. We have about 2 decades of measurements from a series of satellites that actually measure the surface of the ocean. This is called satellite altimetry, and basically it works by shining a laser down onto the surface and measuring the height of the sea surface very, very precisely. With several satellites orbiting the Earth and covering the oceans over time, we can actually get a global estimate of sea level that's very, very precise. Over time, here's what the TOPEX satellite altimetry data look like. What you see starting in the early 1990s is that sea level has been rising a little bit faster than what the tide gauge said. And in fact, this is best fit by a line that's about 3.4 millimeters a year, quite a bit faster than what the tide gauges were over the last century. Putting all this together, here you see the satellite data on the left, showing a sea level rise of 3.4 millimeters per year, and the tide gauge data on the right showing that long-term change of about 2.3 millimeters a year. And you can make out that the tide gauge data also show this recent acceleration, although it's not clear if it's continuing. So there at least appears to be some speeding up of the rate of sea level rise, currently about 3.4 millimeters per year. One of the interesting things about sea level rise is that it's not necessarily uniform over the whole planet. As we discussed before, the tide gauge data show differences that are partly due to changes in subsidence or uplift of local land masses. But it turns out there are other effects as well. If you were, for example, right next to the Greenland ice sheet, and let's imagine that the Greenland ice sheet instantly melted by the equivalent of 1 meter of sea level globally. That turns out to be about 1/7 of the total ice on Greenland. So let's suppose that 1/7 of the ice on Greenland just completely melted instantly. We would expect sea level globally average to rise by 1 meter. And that's what would happen, except that, interestingly enough, the sea level right next to Greenland wouldn't rise by 1 meter. It would actually fall by 19 meters. It's kind of an amazing result. It turns out that the reason that the sea level falls locally is because the Greenland ice sheet is so massive that its gravitational field attracts the ocean. Just like the moon pulls the ocean around and creates the tides, the Greenland ice sheet is actually pulling water towards it because it's so massive. When you lose 1/7 of Greenland, that gravitational attraction is diminished. Even though the sea level is on average rising by 1 meter, the local sea level is actually falling because the difference in that gravitational field is very large locally compared to the distal impact of dumping all of this water into the ocean. Here in this cartoon, you see this process. If you just assumed that everything was uniform and it was just a bathtub and you melted a certain amount of ice, you would raise sea level and it would be the same everywhere. But in fact, it's actually not the way it works. On the right-hand side, you can see what's actually happening, although it's exaggerated. The ice sheet is actually attracting, with its gravitational field, some of the seawater, and the sea level is actually tilted so that it's higher towards the ice sheet. When you melt some of the ice sheet, the sea level rises on average, but the gravitational attraction is diminished, and so as a result, the tilt is a little bit less. And so the local sea level falls very close to the ice sheet, even as the average sea level is still rising. My colleague Jerry Mitrovica combined all of our understanding of the physics of sea level rise and came up with the idea of actually being able to fingerprint particular sea level changes. Here's how it works. Let's imagine you had a certain amount of ice melting from Greenland. Jerry can calculate what the distribution of sea level rise would be due to some mass loss in Greenland. And it would have a particular fingerprint. So there would be a certain pattern of sea level rise that you would see globally if it were due to melting of Greenland ice. Similarly, Jerry can do this for all the different sources of ice. So he can do the same thing for Antarctica. There's a particular pattern of sea level rise associated with ice loss from different parts of Antarctica. And the same with Greenland, and of course the same with mountain glaciers as well. Each of them has a characteristic pattern that is like its fingerprint. And there's one other footprint as well, which is the thermal expansion of seawater. From Argo float data, we actually have measurements of the ocean heat content at least down to about 2,000 meters. And so we can describe how the ocean has taken up heat and how that varies in different parts of the ocean. That also has a particular fingerprint. And so we can calculate how the ocean heat uptake manifests itself in a particular distribution of sea level change. If we combine all of those things and look at the actual satellite data that measures sea level rise, we can try to separate the different components. We can try to tell how much comes from melting of ice on Greenland, how much comes from melting of ice in Antarctica, how much comes from thermal expansion of seawater, etc. This is a really powerful way of using the observations of the geographic distribution of sea level rise and then connecting them to particular causes.